This video is going to teach you how to repair sundown SFB monoblock amplifiers, but also Ground Zero GZZA, Def Bonds Apocalypse, B2 Riot, Bassface Team, and all the other Chinese clones of the sound digital circuit that you see looking like this. And you can also use this information to repair the sound digital circuits these are based on themselves. Here's a list of the tools you're going to need to get the job done. A basic cheap multimeter just to use, mostly as a continuity tester, so it beeps when you touch the wires together, but also for basic ohms measurements. You don't need anything super crazy accurate, just a cheap basic multimeter. A half decent soldering iron, at least 60 to 80 watts, the more the better, and go for a kind of angled flat tip. Gets good surface area on the part you're trying to heat. An adjustable hot air gun like this, that you can get them called rework stations, rework heat gun. Larger nozzles tend to be a little easier to work with and needs to be adjustable for pressure and temperature. An oscilloscope. Yes, you absolutely are going to need an oscilloscope for this. You can't just do this repair with a multimeter. You don't need anything crazy. 60 megahertz is the lowest that I would use for an oscilloscope, and you can use a handheld one, you can use a benchtop one. It doesn't have to be crazy, but if you don't have an oscilloscope yet and you buy one for this task, then you are going to love having one, because it's going to open up so much more possibilities, and you're going to love using it for all sorts of things in the future, and you're going to be able to fix so many more things with it. So if you don't have an oscilloscope yet, grab one. Facebook Marketplace, doesn't have to be crazy, just something. A current limited power supply of some kind between 10 and 14 volts. Generally it's best to stay between 10 and 12 volts because the rail voltages inside the amplifier are lower when you're using it. I have a bench lab supply that you can set the current and the voltage on, but you don't need that. You can get away with using an old PC power supply. The lower amperage the better, really. These amplifiers don't need more than sort of 3 or 4 amps to kind of power up and idle, and that's all you need whilst you're repairing it. So try and stay under 10 amps if you can, somewhere between 10 and 12 volts. And that can be like an old power adapter, like for a charger, or just some power adapter that gives you between 10 and 12 volts and up to about 10 amps. Some rosin core solder. Now you want to get leaded solder, obviously, don't eat your sandwich after handling it, but the lead-free solder is absolutely rubbish. You want like 60-40 or whatever the other 33-67, whatever it is, but you want tin lead solder that is rosin core, and don't cheap out on it either, because it will just be a nightmare to work with. You also need some solder flux. This is going to make your life so much easier when soldering these small surface mount parts. This here is by Chip Quick. You want some decent flux, and ideally some no clean flux. A lot of flux goes conductive once it's heated, so try and get some no clean flux, and Chip Quick is one of the best brands that I've found. Decent sharp tweezers are essential as well, because you're going to be needing them to take these little surface mount parts off the board, and having a decent accurate tight grip on these parts is essential. It's also really useful to have some 99% isopropyl alcohol in a little spray bottle as well, for cleaning up any thermal paste or any kind of burned marks and getting rid of any flux that's left over on the board. And obviously a basic screwdriver, but any other bits along the way I'll cover as we repair this. First thing I'm going to do is go through how this works, so pay attention and feel free to watch this part of the video back as many times as you like to grasp it. Let's start with the power on sequence. So provided you've got 12 volts and ground on the power terminals, when you give 12 volts to the remote terminal, then the 12 volts on signal gets sent to this little circuit here, and what that does is it creates a 12 volt supply voltage that feeds not only the fan that would be here, but also feeds the supply to the MCU. This is the MCU, which is the kind of brains of the amplifier. It's controlling the power supply, protection modes, and a bunch of other stuff. So when the microcontroller receives its supply voltage from the circuit over by the power terminals, the first thing it does is check that there is enough voltage on the power terminals to start with. If there's not, then it will go into protect. It will flash a protect LED, or if it's too high, it'll also flash a protect LED. But if it's within the desired window of operation, then the next thing it does is it sends a couple of little pulses to the power supply FETs to build a tiny bit of rail voltage to make sure there's no output side shorts. And the way it does that is it sends a couple of pulses on these pins here through these resistors, these 100 ohm resistors, and these pulses will be push and pull pulses. They then get sent through these resistors to the power supply drive buffer. Now this chip right here is a 4427 or any other pin compatible MOSFET driver. So it takes the push and pull signals from the microcontroller, applies them to 12 volts, bolsters them up a bit, and then sends them all the way over to the other side of the board to the corresponding banks of power supply MOSFETs. Now per transformer there will be push and pull banks. So for this one transformer we've got 1, 2, 3 MOSFETs in push and 1, 2, 3 MOSFETs in pull, and they'll each receive the push or pull signals from the drive buffer from the microcontroller. So we've got one transformer push pull set up there and another one over here. So those little pulses will be sent to the MOSFETs and will start energizing the primary winds in these transformers, which will then result in a higher voltage on the secondaries. The AC from the secondary winds is then rectified by these rectifiers here for that bank and here for that bank, and then sent to the rail capacitors for buffering and storage. Now the tiny pulses sent from the microcontroller at this stage are just for a health check, so they're very, very small and they're only designed to build a tiny bit of rail voltage. In the microcontroller then senses that rail voltage being built through this voltage divide circuit here, and provided rail voltage is actually being built, then it will continue with power up. However, if it doesn't detect any voltage through this voltage divider, meaning that there isn't any rail voltage being generated because maybe it's being shorted to ground due to an output section fault, then it will shut down and flash a protect LED. However, provided rail voltage is built and it's detecting that, then it will send much wider pulses through to the power supply MOSFETs, building full rail voltage on the output section. In addition to the microcontroller doing this health check and startup sequence, the moment you apply the remote, another couple of things happen. We have this circuit down here, which is a boost convert circuit, and another identical circuit up here, which is another boost converter circuit. Now what these do is they generate the supply voltages for the low side drive buffers on the output channels here. So this is a low side drive buffer that's being supplied by this boost converter, and up here this one on the opposite side is also being supplied by this boost converter. And what needs to happen here is you get a little bit of voltage, I think it's about 5 volts on this boost converter IC. That then creates a bunch of pulses, and in conjunction with the inductor and some capacitor and diodes here, it creates a higher voltage which is used by these drive buffer ICs. The identical circuit up here is creating a similar voltage that is utilized by the preamplifier opamps and also the drive ICs on the output section themselves. So you've got two separate boost converters, one up here and one down here, and these come alive the moment you apply the remote to the terminal. And since the boost converters are alive, that also means that the drive ICs, drive buffers and preamplifier circuit and basically everything else is up and running and ready to go once rail voltage is built and stable. Now because everything here comes alive the second you apply the remote, that would mean that the output MOSFETs and everything here would start trying to oscillate as soon as you apply the remote, which is not ideal because rail voltage hasn't been built yet. So what happens is the microcontroller actually locks these drive ICs into shutdown mode through these two diodes here initially while the microcontroller is doing its startup procedure and generating rail voltage. Then only when it detects that full rail is built through this voltage divider, then it allows these drive ICs to finally activate and start switching the output MOSFETs. If we follow the signal in through the RCAs, we have 3 opamps which are TL074Cs here, and these will be responsible for controlling the low pass filter, high pass filter, gain and bass boost that these amplifiers for some reason seem to have. And once the analog audio signal has been processed, it then gets sent to this chip, which is an LM319, to be converted into pulses for Class D operation. Once the audio signal is in pulse form, it then gets sent to the Class D drive ICs, and these are IRS 20957S drive ICs. This processes those pulses and gets them ready for Class D switching, so it will generate a high and low side pulse. It'll apply dead time and any duty cycle changes that you've set using the resistors and capacitors around the IC. Then these chips could drive the MOSFETs directly. However, in this case, the designers have chosen to buffer the output drive signals from these chips by some final drive buffers, just to kind of bolster them up a little bit perhaps. So we have 2 little 6-pin ICs right here, and these themselves are what drive the output MOSFETs. And we have 2 low side and 2 high side MOSFETs, and these work in bootstrap. So these are all N-channel MOSFETs, and it's using the high side supply is generated from the low side switching through a combination of a diode and capacitor to act like a pump, if you like. So because this is a full bridge amplifier, we have essentially one channel over here and another channel over here here, and the signal sent to each of those will be 180 degrees out of phase with each other. So once the PWM version of the audio signal is applied to the high voltage rail by these output MOSFETs, it's then sent through this inductor and capacitor network to get rid of the high frequency element, which is how Class D works, leaving you only with the low frequency audio waveform that's then sent to the speaker terminals over here. Now you've got some idea maybe how it works, let's start getting to how to repair one of these when it's blown. The first thing you want to do obviously is take the back off and first look for visual signs of failure. Typically you won't always get any visual signs of failure on the output side. Even though it can be completely blown internally, you won't necessarily always see visual signs of failure. We do in this case, but often at times you won't see visual signs of failure on the output side. However, on the power supply side, because the power supply MOSFETs are connected directly to the 12 volts and ground across them, if anything shorts over here with these MOSFETs, then they get full current available from whatever power supply, batteries, alternators you've got connected, and they absolutely cook. So if you open the amplifier and you see loads of black, brown, burns, soot marks, etc. over by the power supply FETs and the transformers, then you've got a blown power supply section. Now power supply sections are relatively easy to repair in most amplifiers, and particularly these amplifiers. If you have all black and blown power supply MOSFETs, here's what you need to do. Firstly, cut out all of the power supply MOSFETs. Even the ones that look maybe okay visually, you can't reuse them. So cut out all the power supply MOSFETs from both sides. Do not cut out the rectifiers in the middle of the board or the output MOSFETs just yet. Then take a good close look at the gate resistors. Connected to leg 1, which is the gate of every single power supply MOSFET, you will find a gate resistor. This is typically a low value resistor. Now when the power supply MOSFETs short, they send 12 volts from the middle leg back through the gate path to ground, burning out the resistor. So you want to check every single one of these gate resistors, and to be honest, they're very cheap, so it's a good practice just to replace all of them anyway. But if you want to check them, take your multimeter, touch the multimeter leads together first to get your test lead resistance. In my case, you can see I've got about 0.5, 0.6 ohms. Then go across the resistor and make sure it's within tolerance. So 10.4, that's pretty much dead on 10 ohms, that's absolutely fine. You might find your amplifier has 4.7, 10 ohm, 22, 47, but it will be generally under 100 ohms. You just want to go ahead and make sure that these are all reading within a tolerance. Now the way to read the value of a surface mount resistor here, to make sure you're reading it correctly, the last digit, the last number, is always the number of zeros after the first two numbers or the first three numbers. So in this case, these look like they say 100, but that is just 10 with 0 zeros, therefore it's 10 ohms. If it was 101, that would be a 100 ohm resistor because it would be 10 and then 10, which is 100. And same for 103 would be 10,000 ohms. If these are blown, burned, or reading the incorrect resistance, then you need to remove them. You can either use your hot air gun to heat and melt the solder and then pick them off with your tweezers, or you can take your flat tip soldering iron like this, get some fresh solder on the tip, and then just kind of wipe it on the top and pull, and generally they'll come off on your tip, which you can then wipe on the desk or something. And then when replacing these, make sure that they've got fresh solder on the pads from your nice 4060 or leaded solder that you've bought. Then a tiny little bit of solder flux just on the pads that you're going to replace, and then take your new resistor, hold it with the tweezers in place, and then with your heat gun wiggle around, melt the pads, and then it will snap into place with the solder flux. It's very satisfying. Then you can just let go of it and then let it cool. Once you've cut all of the bad power supply MOSFETs out and you've checked or replaced all of the gate resistors by the power supply FETs, then you can turn your attention over here to the power supply MOSFET driver, which is over here. It might be marked with C2, but it's a 4427 all pin compatible MOSFET driver. There's literally loads of them. Now this often gets damaged when the power supply FETs blow, and we can see if it's damaged by powering it up and see if it sends pulses, but a quick check is to see whether the 10 ohm resistor, which is in line with its supply voltage, is damaged or not, which is right here. If that is reading open or it's blown, then your drive IC will be bad and you'll need to replace that as well. However, if you get the correct resistance across the 10 ohm and there's no short on the resistor here to ground or low resistance to ground, as you can see here, it's just charging a supply capacitor, chances are your drive IC may have survived, but you can use the oscilloscope in a minute, which I'll show you to check that further. So if you've determined this might be okay, or you've replaced it if it was obviously blown or shorted, next thing you want to do is connect some power to the board, and we're going to see whether the MCU and the driver has survived or is working correctly before we fit new power supply MOSFETs. It's very important. And for this test, you don't need barely any current whatsoever. So your 12 volt supply can be like 1 amp or something like that. It's absolutely fine. And now this is where you're going to need your oscilloscope. So we want to read the pulses coming from the MCU through the power supply drive buffer to the power supply MOSFET pads. So on your oscilloscope, you want to set your voltage divide to 5 volts, which is the scaling height-wise on the screen between each grid line, and time divide you want about 10 nanoseconds. 10, it looks like a little U, 10 US, and that is the scaling width-wise. Depending on how your scope works, other useful settings will be perhaps noise rejection on or off, see what looks better, reject low frequency or high frequency. You want to DC couple the trace as well rather than AC couple it. But once you start reading one of these waves, you can have a play around with your scope settings to try and get it locked in and stable on the screen. So you've got 12 volts at the power terminals ready to go. Your remote is ready to go. I use a foot pedal to turn on and turn off the remote. I find that super easy. It means both your hands are free to probe around and stuff while you're on and offing the amplifier. And because you haven't got any power supply MOSFETs fitted, the amplifier is obviously going to go into protect because it detects there's no rail voltage being built. So you're going to need to keep sort of pulsing the remote so you can see those drive waves going to the power supply MOSFET pads every time before it protects. So take your oscilloscope probe, and first of all, remember that you've got push and pull banks, 3 FETs per each. So first of all, probe pad 1, which is the first pad here, which connects to the gate resistor of the push bank, and have a look at your oscilloscope as you power up the amplifier with the remote wire. And what you want to be looking for are some pulses that look something like this. Tiny little, very low duty cycle pulses, and that's the kind of health check mode the amplifier does to build a little bit of rail voltage. So if you have them on the push bank, then go along to the pull bank over here, make sure that they're present on pad 1 as well. Yep, that looks good. So if you're missing one of these, or it looks bad shape or is a different height to the other one, then chances are you've got a damaged drive buffer. Now what you can do is you can check the waveforms going into the drive buffer to make sure that it's getting both of those. So you can go ahead and check pin 2 here. Have a look on your scope. Now the waves will be smaller, so you can go down to 2 volts divide on the scope here, so they look a little bit bigger. There we go. There we go, so we've got input to the push bank and input to the pull bank there. So if you get them here going into the drive buffer, but you don't get them coming out of one of the banks, then obviously you have a bad drive buffer. However, the worst thing that can happen is if you don't get one of them going in. So let's say we were missing the pull set of pulses here. If you're not getting one of these sets of pulses going into the drive buffer, then the MCU here, the microcontroller, has been damaged, and unfortunately it's very hard to get hold of because you can't just replace this because it's been programmed at the factory with all of the parameters and everything it needs to work. If you just replace that chip, even with the correct number, then it won't work because it will just be blank, it won't be programmed. So yeah, you might need to get in contact with the manufacturer, see if they can send you an MCU, but from my experience it's very difficult to do that. But hopefully you do have your pulses on the inputs to the drive buffer here, and you can just replace the drive buffer so that you get those pulses being buffered and sent over to the power supply FETs here. Once you have good shape and equal pulses on both push and pull banks of all of the power supply gate pads, then you're ready to move on. Now you could fit some new power supply FETs at this point. However, this is quite a convenient point in the repair to take a look at the output section, because you can do some stuff here and get the output section kind of up and running without the scary high voltage rails being there for you to accidentally slip and mess up something with, or to burn out some components. So leave the power supply FETs out for now. I can't do that obviously because they're already all fitted, but we're going to turn our attention to the output section. Now for the output section, like I said, you're not always going to get visual signs that there's any damage over here. So what you want to do is take your multimeter and you want to put it on the setting where it gives you an audible beep when you touch the probes together. So because these output MOSFETs can be internally damaged and shorted but show no visual signs, you can go ahead and check between all 3 legs. Now remember, Remember not to check the rectifiers. These will always read a low resistance or short between legs 1 and 3, but never legs 1 and 2 and 2 and 3. So don't get confused into thinking you've got a dead part by checking the rectifiers here. It's the output MOSFETs you want to check. So start off firstly by checking between legs 1 and 3. On the multimeter, you will have a sort of mid-high number one way round, and you can flip the probes around the other way and you'll get a different number usually, or not always, but depending on the amplifier, you'll get a slightly different number each way round. And then check between 1 and 2. Make sure there's no low resistance or short, and check between 2 and 3. Make sure there's no low resistance or short. So check all of these output MOSFETs over here, and then move along to the other side. Okay, so we can see here that we have a low resistance between 1 and 2, low resistance between 1 and 3, and between 2 and 3 as well on these ones. This one here actually does have visible damage. It's got a break in the leg here. That's shorted. That one there is shorted as well. And that one there doesn't read quite as low of a resistance between 1 and 3, but it's still reading a short between 2 and 3 there. So where these amplifiers are full bridge, there's essentially 2 channels here. So in my case, I've got one channel over here with no shorted output MOSFETs, but one over here that is quite heavily damaged. So depending on how this amplifier failed, what you were doing at the time or what was happening, you might actually have one channel that's absolutely fine with no damage and no stress, and the other channel which just needs a repair. If you're unsure and you're getting the parts anyway, it's not a bad idea just to replace all of the output MOSFETs when you get around to doing that anyway. But in this case, I know for a fact that this channel is absolutely perfect, and we'll get to that in a bit when I show you why this amplifier failed. But if you do find shorted output MOSFETs, then you can go ahead and cut them right out of the board. Now, even if you only find one shorted output MOSFET in a certain bank or channel, then you need to replace all of the output FETs in that bank anyway, because chances are the ones next to it, even though they might read okay and they might even still operate okay, are very likely to have been damaged in the event that caused them to fail. So we're just going to cut all of those out on this whole channel and get rid of them. Now, with the dead output MOSFETs removed, we can turn our attention again to the multimeter on diode setting, which generally beeps as well. And what we can do is take some measurements of the bad channel and the good channel. If you had 2 bad channels, then you can do this as well. And if you have one looks like surviving channel and one bad channel, you can do this, and it will help you to determine the health status of the drive circuit. Now in my case, it's quite obvious, we have some visual signs of failure here, but I'm going to pretend that that's not there and pretend that it just looks okay, so I can show you this. So the first thing, if you've got a channel that looks like it might have survived, then turn your attention to here first and just get some rough ideas of what the values are between legs 1 and 3. Don't worry about reading 1 and 2. We're reading 1 and 3 because 1 is the gate leg, which is going to be connected to the drive circuit here, and 3 is generally the ground reference for that bank. So we're just measuring between gate and ground, essentially 1 and 3, and we're just getting a rough idea of what the values should be. So with the probes one way round, we get about 618, and the other way round we get about 623. So that is on the, I think, low side here, and on the high side we have 632 and we have 890. So that's what we're looking for on the other side. They should be near on identical, provided that this drive circuit is okay. So if we go between 1 and 3, okay, we have a very high value there, 1633, and if we flip the probes round, we have 597. So that's very different to what we read over here, and that's not because it doesn't have a MOSFET in it. The MOSFET won't really read anything between gate and source on the multimeter like this, so that's because we have something wrong with the drive circuit. Let's check on the other bank over here, which I think is the low side of this bank. So we have nothing at all on that one, nothing at all here, so that's obviously different to the period working channel. Flip the probes and we have nothing that way either. So it's quite obvious that there's very different readings, therefore we almost certainly have some drive circuit faults over here in this bank. So let's zoom in on the drive circuit and let's work our way back. So these 2 chips are the buffers for the drive signal coming from the drive IC. So these drive the MOSFETs directly. So these things are the first thing that's going to get damaged in the event of a MOSFET failure, which you can see right here. In addition to, similar to with the power supply FETs, you might have blown gate resistors, which are in line with the gate leg, and also blown diodes. These have diodes next to the gates to help turn the MOSFET off quickly on the down pull of the drive signal, and we've got some visual failure there, but they can also be damaged, which I'll explain and go through a bit later. But let's first of all take a look at the drive buffers. So obviously in my case we have some visual signs of failure. Now if you get different readings on the legs here, then the first thing you want to do is just remove these and replace them. So to remove these, we're going to drop some flux on the legs, not too much, just a tiny little bit, just helps them to come off, and get our heat gun on, and we're going to choose a temperature. Your heat gun will vary because the temperature that the heat gun is set to is not the temperature of the air coming out the nozzle, because it gets cooled as it comes along. It depends how far away you hold the nozzle from the part. So just kind of get to know your heat gun and what temperature and pressure works for you. But on mine, I set it to about 420 to 430 degrees Celsius, and the pressure, it's not in PSI, but my screen says about 32. Once your gun's up to temperature, just start drawing circles around the chip here. You want to preheat the surrounding board a little bit. It'll prevent popcorning of the PCB, where you're heating a specific area for too long and the air under the layers heats up and expands and causes the kind of board to bubble up and popcorn. So you just want to kind of draw circles around it, get some heat into the surrounding board. Then once you've preheated a little bit, you can focus some energy on the IC itself, and comes straight off. So let's get rid of that one, and let's do the same for this one. There we go. You can put those straight in the bin. Now in my case, I've got a visually failed capacitor, C72. This is a tantalum capacitor, quite rare for these to fail actually. You don't usually come across this. But these capacitors, if you read them, the camera won't be able to make it out, but it says 106. So that is 10, so it's 10 with then 6 zeros after it, and the voltage is 63 volts. Now if you're replacing the drive buffers, it's a good idea to check the resistors that lead between the drive buffers and the drive IC, which is the 20957S. So in my case here, a 10 ohm resistor, so this one right here is reading 11.1. Now there is some heat in the board, so that could just be the resistance has increased because it's kind of hot, so I might replace that anyway. But this one here has some visual signs of failure, and it's reading kind of high as well. So if these 10 ohm resistors here that lead between the drive buffers and the drive IC are either out of tolerance or visibly damaged, then you obviously want to replace them, but the chances are that it's damaged the drive IC as well. Now you won't always get these resistors burn out when you have a damaged drive IC, but that is a sign of it. So I'm going to go ahead and remove the drive IC as well anyway. And to be honest, chances are if the drive buffers do read damaged when you check the legs where the MOSFETs were, then the likelihood is that the IC is also damaged. So if you're replacing the drive buffers, it's good practice just to replace the drive IC at the same time as well, to save yourself some headaches. Now, this is a large chip, so you do kind of want to draw circles around it, and you want to heat it evenly, heat a little bit the board around it as well. And just be patient, don't pull hard on the chip, you'll rip the pads up. Just be really patient. When it's ready, it'll literally just come off like that. We're also going to replace the two 10 ohm resistors, one there and one there. And while we have the heat gun on, we're also going to go over here, and firstly I'm going to remove this clearly visibly damaged diode over here, and I'll go through what all these are in a bit once we come to that. Now the fact we have a damaged drive circuit, I suspect the gate resistors over on this side might also be out of tolerance, especially in this bank. So these are actually 13 ohm. Now if you can't find or buy 13 ohm, they don't have to be exactly the same. Gate resistors can be within a sort of tolerance of what they should be. So if you can't find 13s and you're replacing all of them from both sides of the amplifier, you could use 10 ohm, 15 ohm, probably get away with 22 as well. They don't have to be the exact same value down to the last number. If you can't find 13s and you've got a bunch of 10 ohms on hand, just use the 10 ohms, it's not going to be a problem. 13.7. Remember, I've got a bit of test lead resistance. Here we go, I've got 0.8 ohms of test lead resistance now actually, because this is a pretty cheap leads. So that's dead on 13. That one there is completely open, and that one there is completely open as well. So we need to replace both of those 13s. Now while we're over here, I'm going to take the regular iron and remove the legs from these MOSFETs that we cut off. Now I'm doing all this from the top of the PCB. This isn't the best practice. You're best off removing the PCB from the heatsink entirely and doing this from combination of top and bottom to get the heat into both sides. But because I've done this so many times, and because I don't have a power supply section failure where I've got like loads and loads of FETs to replace, and also there can be the chance of a blown trace on the bottom of the PCB when the power supply is blown, but not really the output side, I'm saving the customer for this amplifier some money by not charging him the labor of me completely stripping the entire board down unnecessarily, when I know that I will just need to replace some parts on the top of the board here and these 4 MOSFETs. But if you're doing this and this is your repair, or you're less experienced or you're unsure, always strip the board down entirely, and it makes it a lot easier for soldering as well when you're a little bit less experienced. Then we can suck the remaining solder from the holes. That's one tool I forgot to mention earlier, is a solder sucker. I just use one of these super cheap spring-loaded suckers, but you can get a bit more fancy if you want with an electric one or a bigger one. But I find that these cheap ones work absolutely fine, especially with a silicone tip on the end. They don't come with that, but you can buy a little bit of silicone hose, just get the right diameter. It makes these work a lot better. So in order to suck the remaining solder from the holes, you can actually apply more solder, which sounds counterintuitive, but it actually will help you to get all of the solder out of the hole, because it's new fresh solder that's probably better quality than what you used in the factory, and there's more thermal mass there. So you just heat it up and then suck it away like that, and you have nice clean holes. Now this is where your isopropyl alcohol is going to come in handy to clean off the thermal paste. From here, so we can apply some fresh new stuff. Now, in these amplifiers over by the output MOSFETs, you will find 2 different sets of diodes. In parallel with the gate resistor, there is a 1N4148 diode, and what that does is it provides a low resistance path for the energy that's stored in the gate to ground when the drive signal asks the MOSFET to turn off, because you want these FETs to turn off really fast. So you don't want the energy that's stored in the gate, that forms part of the gate capacitance, to go slowly back through the gate resistor. You want it to go nice and quickly to ground through the diodes. So that's what the diode is for in parallel with the gate resistor. It provides a bit of dampening for the drive wave on the way in, but then a nice quick path for the drive out. So these can be damaged when the output FETs fail like this, and that's what I experienced here with D36. This 1N4148 was bad. Now these other slightly larger diodes are 15 volt zener diodes, and they can sometimes be 18 volts in different amplifiers, but in these ones they're 15s, and they basically prevent the voltage on the gate leg exceeding the zener value of 15 volts there. So it kind of clamps the drive wave voltage to 15 volts, and that just keeps everything nice and stable and cooking. And these can also fail when the output MOSFETs fail as well. Now the problem is that these diodes are quite difficult to read when they're in circuit, and that's because the 4148s are obviously in parallel with the gate resistor. So when you take your multimeter, you're just reading the gate resistor rather than the diode. And the 15 volt zeners, because they go from the gate to the source, when you try and read one of them, you're essentially reading all of them through the gate resistors. So in order to read each diode correctly and individually, one tip you can do is actually to just remove or lift each of the gate resistors so that none of the 15 volt zeners are connected to each other, and so that the 4148s don't have a resistor in parallel across them. So we're just going to do that with these 13 ohm gates here quickly. We're just going to remove them from one of their pads, just so we don't lose them. This black adhesive is super annoying, it's really in the way here. Okay, there we go. Okay, so with those resistors just knocked off their pads, that then allows us to read each of the diodes individually. So if we read this 4148 here, you can see we've got 550-ish one way round, and we should get nothing the other way round, because that's a diode. You have a voltage drop one way round and then nothing, because it doesn't conduct the other way. So you just want to make sure that all of these 4148s are the same. I suspect this one is fine because it was part of the good bank. It's kind of hiding a little bit under that capacitor. I don't think I can get to the other pad, but that one's probably going to be fine. So we're interested in checking the ones over here that were bad, on the bad bank if you like. So we've got, okay, so we're not reading anything on that one with the probes either way round. Now that would have just read fine with a gate resistor in parallel with it, because you wouldn't be able to read the diode, but it's open, so that needs to be replaced, because that won't be pulling the drive down to ground as quickly as the other banks, which is bad. Okay, so we know we need a new 4148 there. Let's check the 15 volt zeners. So again, a similar kind of thing. You want a value one way round, flip the probes, and you don't want to see anything the other way around. If you see a value both ways round, then the diode's probably bad, or if you see nothing, then the diode's probably bad. 652 and nothing. Okay, let's check these ones that were from the bad bank. Nothing that way round. An easier way actually is just to read across gate and source pads, because that's what the diode is connected to, so it's nice and easy. Okay, that 15 volt zener is also open, so we're going to need a new one of those, and that would have been very hard to read as well with the gate resistor in place. And so is that one. So we need 2 replacement zeners, 2 replacement 4148s, and new gate resistors all around, but these ones here are absolutely fine. So I'm just loading up some fresh solder onto these pads that we've removed already. And let's remove these 15 volt zeners. Fresh solder. Okay, so let's find some replacement parts. So firstly, we've got a couple of 4148s, and then, if I remember rightly, these are 15 volt zeners. Now they're a slightly different package. You can see these are glass package, but it doesn't matter what they look like, it's just to do with what spec they are, what kind of diode they are. So these are the 15 volt zeners I've got at the moment, so I'll drop those in. Now obviously, being diodes, their orientation is absolutely critical that we get them the correct way around. So going by the marking of this one, the slightly curved part of the silk screen is where the line is. So we want to line that up there. And then these are very, very hard to see, so just going to try and take a look. Now if you're unsure, the side of the diode with the line on it needs to be connected to the pad coming from the drive circuit. So the part of the diode without the line needs to be connected to the MOSFET gate. Drop some fresh flux around here. Drop this zener in here. So the 4148 needs to conduct coming out of the MOSFET gate, not going in. So we need to have the voltage drop reading across this way from here to here, which we do, and it needs to block going that way, which is correct. So let's check this. We've got the correct way around here, so that's coming out there, so we need to go there. We need the voltage drop reading that way round, which we do, and block that way. Excellent. So I got these in the correct way round first try. That's excellent. And for the zeners, we need the voltage drop reading from source to gate, so with the red probe on source. So let's make sure we got that correct as well. Yep, we did. I've just gone to read this one, but I'm not getting a reading either way around, which doesn't make sense. Across the diode, we do have a reading there, as you can see, but it's not across here. So that means that we have a broken connection somewhere. Now these two source pads should be connected together, but they're not. Okay, so this is actually super rare, but it might be a good thing to note. So in this case, because I know what to look for, we do indeed need to strip the board from the heatsink, because it looks like we have a broken trace on the underside of the PCB. That's not very common to happen in these amplifiers, especially on the output section. It can happen on the power supply section, which is why I said if you have a blown power supply, just remove it all from the PCB anyway, but super rare to happen on the output side. So let's get this out of the heatsink and repair the broken trace that we're going to have on the underside there. Actually, just quickly, while this is all hot still, I'm going to just replace these gate resistors with some spare. I do have some 13 ohms here, so we're just going to drop those in. If I didn't have 13 ohms, then I'd just replace all of the output gate resistors, probably with 10s. You see it just snaps into place, really satisfying. Okay, what does this look like underneath? Oh yes, we have a fuse trace, nice. I suppose it's probably always a good idea to remove the PCB from the heatsink anyway, but I've repaired so many of these boards, this is really, really rare when you've just got one side going down like that. So yeah, as you can see, we have a blown trace here leading to that source pad, which is what we were seeing on the top of the PCB. We also have this trace has taken a hit. It's not blown, but it's got hot there because the solder mask has chipped away where it's got really hot, but the trace there is actually still perfectly intact, but the heat has just bubbled away the solder mask. So it might be tempting to bridge over that break with some solder, which you can do. Solder doesn't really have the lowest resistance ever, but it is a very, very tiny gap. And the output section here is using higher voltage, lower current. But sometimes the solder mask will prevent you from really getting a good bridge. So the best way to do it is just to take a piece of component leg that you've cut off. I always keep a bunch of pieces of component leg laying around spare, and yeah, then you can just bridge the gap by soldering a piece of bar across. Let's get it out of the way of the hole, like so. There we go. So now if we turn our attention back to the zener diodes, we should be reading this the correct way around. So let's confirm 572 that way round, 571 that way round. Yeah, that's correct. Excellent. So we have the diodes in the correct orientation. We have new gate resistors fitted. So let's just clean this area up with a old toothbrush, which is another good tool to have on hand on the bench. Get rid of any solder flux and stuff that's remains on the board from working on this area. Okay, so at this point we can actually fit some new output MOSFETs. Now in other amplifiers, especially older ones, then you don't really want to do this yet, because you can test the drive circuit by powering the amplifier up without the output MOSFETs fitted and checking for drive waves. However, with 20957 based amplifiers and IR2092 based amplifiers, they don't actually give any pulses when the output MOSFETs aren't fitted. It's kind of a feedback thing. It kind of detects that there's nothing there, and it doesn't actually pass any pulses out of the drive IC, so it's very hard to tell. So having FETs fitted is what you're going to need anyway to test it, and we might as well do it at this point, because then we can use the multimeter to check other things. Do not, whatever you do not buy your parts from eBay, Amazon, AliExpress, dodgy Chinese websites. You need to buy your parts from a reputable, known retailer of genuine electronic components. In America you can find Mouser, DigiKey, RS Components. I think we have RS Components in the UK, Farnell, etc. Places like that stock genuine electronic components, and yes, they're not going to be cheap. I think these MOSFETs over here in the UK can be sort of £4 or £5 each, which might be like $6, $7 or $8 each over in the States. But that's just kind of what you're going to have to pay. Don't be tempted by some eBay 4227s that are like $1.50 each or something like that, because they're going to be fake. They're not going to be 4227s inside, or they're going to be rejected batches that have quality control issues, and you're just going to have to do these repairs all over again when they fail. So stick to your genuine parts. Yes, you're going to have to pay a bit more, but it's worth it in the long run because it's going to work. I like to just tack the gate in place from the top of the PCB here, so the FETs don't kind of fall out when you flip the board upside down. Now when you're soldering, you want to make sure that you're holding the iron on for a decent amount of time after the solder has flowed and made a connection between the leg and the board, just to make sure that the solder is seeping through the via to the top and bottom side of the board. If you let go too quick, you'll end up with a kind of bit of a cold joint. Just hold it on there for a bit, make sure it's really hot, nice and wet, and it soaks through from the top to the bottom. All done. Now we can just trim these legs. So now let's turn our attention to the drive circuit. We've already removed the drive buffers and the drive IC. Now with our multimeter, it's a good idea just to go ahead and check, because it's quite quick to do this, any other semiconductor or silicon components here around the drive circuit. There's not many to check, so just put your multimeter on diode beep mode. Make sure that none of these diodes here either read the same low value both ways round or beep on the multimeter. So we're looking for sort of mid-range values one way around and either a high value or completely open the other way around. As we're getting with these, that's good. That's good as well. That's good. Okay, we have a high value, 16 on the multimeter that way round. And this way round, we have nothing. Okay, so this diode here, good job we checked. This is another 15 volt Zener. That one's bad because it should be reading the same as the other 15 volt Zeners around here. This is a 15 volt Zener, so you've got 659 one way round, then open the other. Whereas this one here is reading nothing that way round and high value. As it changes, not reading anything now. Yeah, it's basically not reading what it should. It's reading a high value that way round and open that way. So we're going to have to go ahead and replace that one as well. These are all 15 volt Zeners along here. Now, we haven't actually spoken about why this amplifier failed. Now, there can be a whole bunch of reasons that these amps fail. Sometimes the MOSFET just gives up. They run very close to their limits in these amplifiers, voltage-wise and also current-wise. Maybe it was a user error, maybe it was vibration damage, but in this case, it has an interesting reason for failure. Let's take a look. So, as you can see with this drive circuit here, we have the inductor. Now, the inductor is seated to the board with this kind of silicon adhesive stuff, and it's spilled over when they've been applying it, this 15 volt Zener here. Now, unfortunately, the adhesive that these factories are using at the moment appear to emit some fumes that actually break down the solder that's used. I think there's probably lead-free solder. So the fumes from this adhesive breaks down the solder, and as a result, the adhesive that's spilled onto this Zener diode has broken down the solder, and therefore this diode is no longer connected to the board. Now, I can't remember exactly what this diode was responsible for. It's a 15 volt Zener, but we can check in a bit. But given the fact that this diode is no longer attached to the board, it's going to need to be there, otherwise why would they fit it in the first place? We can check what it does. I think it might clamp the voltage coming out of this drive buffer perhaps. So given that that was not connected to the board and we have a meltdown on this side, I would say that that has caused the failure. It's not being fitted. If you take a look at the other channel, the other side here, you can see that there's loads more spillage over even more components on this side. But this channel still seems to be up and running. There's no damage or bad parts that we've read over this side. However, we're going to need to remove all of this to prevent the same thing happening which happened on this channel to this one. So there's going to be a bit of work because this stuff is not the nicest stuff to remove. You can heat it a little bit, try and chip it away without damaging the components, but that's going to be a bit of work to get that off. But in any case, the cause of failure is almost certainly the fact that this diode became detached from the board, therefore something went out of whack and killed these bank of FETs. So we're going to want to put a new Zener diode in this location here, and we also need to replace the tantalum capacitor here, which is a 106 63 volts. We need new 10 ohm resistors in here between the drive IC and the buffers. We need to replace the buffers in the drive IC as well, and that should be everything in terms of replacement parts over here, because we checked all the other diodes and they all seemed fine. Let's just get rid of that bit of soot on the board there from where the drive buffer exploded. There we go. So let's try and get this diode out of here so we can refresh those pads and cut away that adhesive enough that it doesn't happen again. Although the solder that we're using is lead solder, so it might not be affected in the same way, but we don't want to take any risks really, do we? That's that diode removed. Fresh solder on all of these pads, and I'm also going to freshen up the pads for the for the drive buffers as well. You can just kind of flood these and drag your iron over them. Okay, so first things first, a couple of new 10 ohm resistors between the drive ICs and the buffers. Okay, we need 2 replacement 15 volt zeners. 1, 2. Let's drop this replacement capacitor in place. Time for our replacement drive buffers. Now I will put in the video description all the part numbers for all of these and all the MOSFETs that you would need for various different models. There's a few different options for drive buffers and power supply FETs and power supply drivers, so I'll put a list of parts that you can replace for each bit in the video description here. There we go, and last but not least we need our replacement drive IC, IRS 20957S. There we go, lovely stuff. So there we are, we fitted all of the parts, replaced all the bits that we have measured were obviously damaged, or we could see that were obviously damaged. Now, in order to test this, the worst thing you can do is just plug this into 12 volts or high current and power it up. Okay, there is a much better way to test these amplifiers, and I will explain how. There are 2 diodes in the middle of the board here. Now if you remember back to the start of the video, I mentioned that these diodes connected between the output drive ICs and the microcontroller, and they sit on the signal that tells the drive ICs to remain in shutdown mode from the microcontroller. So while the amplifier is powering up and going through its health check mode, the microcontroller will hold the drive ICs in shutdown mode to prevent the outputs from oscillating until the microcontroller is satisfied that everything is okay, and only then will it release them. By default, without the microcontroller being there, the drive ICs would want to start to activate after a second or a couple of seconds of being powered up there. I think it has an internal pull-up that pulls up the shutdown pin or the activation pin so that the chip comes alive after a small amount of time of receiving supply voltage. So what we can do is, by removing these diodes or just lifting these diodes off the board, we can disconnect that signal from the microcontroller to these drive ICs, and what that will do is it will cause the drive ICs to come alive as soon as they receive power, pretty much, because their shutdown pin won't be being pulled down or pulled up, whatever the microcontroller is doing, can't remember. So that means that even when the microcontroller puts the amplifier into protection mode, and even without any rail voltage or very little rail voltage, the drive ICs will be active, and because all of the rest of the circuitry is always active while the remote is connected, because we have our boost converters over here powering the preamplifier stage, PWM generation stage and the buffer stage, etc., that means the amplifier is going to basically come on as soon as you hit the remote, regardless of whether it's in protect or whether there's any rail voltage or anything like that, and it will actually start to produce audio. This is why at the start I told you not to replace the power supply FETs just yet, because with no power supply FETs fitted, obviously no rail voltage can be generated, which is good in this case because we're going to get the output section up and running without scary high voltage rails and test that everything works okay. In my case, for this repair, since it wasn't a power supply failure, I do have the power supply FETs fitted. So I'm going to show you both methods to get this output section tested safely on low voltage, whether you have the FETs fitted in the power supply or not. But before we do that, remember how in my case I have all of this gunk over here that's covering the other side of the circuit. So I'm going to just start chipping away at this and get this adhesive off of all these components in here. Make sure that the solder joints are good. I'll probably just run over them and reflow them just to make sure that they have a good connection where it's been covered in this stuff, and then we'll move on to powering it up. So before you go putting any power to the amplifier in this state with those diodes removed, it's important that you put a load across the speaker terminals. That's one of the only ways these amplifiers can kind of start oscillating at this low rail voltage that you're going to use. So I'm using a 16 ohm resistor, big bank of resistors I've got here, but you can actually kind of use anything under 20 ohms really. A 10 ohm resistor doesn't have to be very big. You're not putting any power to the speaker terminals, you're not putting any signal into the amplifier, you just want to give the output sections a bit of a load against each other. You can actually even just completely short out the speaker terminals. Just take a piece of wire and short them out. That also does the exact same thing, and it's perfectly safe because you're not applying a signal to the amplifier, so there should be no potential difference between the terminals. So it just needs a bit of a load for each channel to kind of see each other. Now then, to safely power up the output section and test it without having scary high rail voltage, if you don't yet have your power supply FETs fitted, that's cool. In my case, what we're going to do is we're actually going to let the power supply try and power up, but we're going to set a super low current. So you can either set a low current on your bench supply, or if you don't have a bench supply, try and find the lowest current power supply that you can, maybe like 1 amp or 2 amps or something like that. And basically what will happen is the microcontroller will do its health check, which will build a little bit of rail voltage, but then it will shut down because it detects that not enough rail voltage has been built, leaving you with maybe like between 5 and 20 volts worth of rail in here. But even though the microcontroller will shut down and go into protection mode, as long as you have the remote connected still, the output section will be up and running because you lifted these diodes here between the microcontroller and the drive ICs. So all the while your remote is connected, the amplifier will be oscillating or trying to oscillate, and if the voltage gets too low in the rails, because it will start to sink down obviously as the output section is switching, you just give the remote another little pulse, get some more pulses, build a little bit more rail voltage, and I'll show you that now. What we want to do is nice low current on the supply. I'm sticking with 1 amp here for a minute. Actually, maybe I'll just go up to 1.5. There we go, 1.5 amps. And what I'm going to do is probe with my oscilloscope the low side drain. Okay, and what that's going to do, oh, you can see we already have 12 volts there because it uses the 12 volts as the initial part of the rail. That's fine. And the low side drain should have a tiny little bit of DC on it, perhaps, as it should be on both sides. And we're looking for, obviously, Class D switching on the low side drain of both this side and this side. Now to set your scope up for that, you probably want to go for, about 10 nanoseconds divide. I'm going to go up to 10 volts divide on the vertical axis here. Reject low frequency, noise rejection on. Yeah, it looks about right. Okay, so I'm going to press my foot pedal now to send 12 volts to the remote, and we're going to see what happens here. I don't know if I've found all the faults and fixed everything, but we're going to find out and see what it does, and then we'll talk about it. So remote going on now. Okay. We have some PWM. Okay, that's fantastic to see, and let's go over to the other side. We have PWM on the other side as well. So that is Class D switching, and it's remaining active because we removed these 2 diodes, even though there's only a tiny amount of rail voltage. Now, it appears that this specific amplifier, the way that it's been designed, is that it uses the 12 volts from the power terminal to form the basis of the rail voltage. So the rail voltage never sinks below about 12 volts, as you can see here on the oscilloscope. The rail voltage is always at 12 volts, and then even though my foot is held on the remote, okay, it's held down on the remote at all times, the amplifier is cycling in protect, and then it tries to power up again. So if we probe the power supply FET drain, you can see here at the moment there's nothing, and then in a moment it'll do a little pulse. See that? So every sort of 5 to 10 seconds or so it does a little pulse to try and build a little bit of rail voltage, or try and build the required rail voltage for the amplifier to power up. But obviously it's not able to do so because I've limited my current to about 1.5 amps, so it's not able to do that. Every time the power supply pulses, you can see the rail voltage jumps up a little bit. It jumps up from 12 volts where it's resting to about 15-16 volts, and then sinks back down again to 12 because it's being used up by the output section, which is currently oscillating. The oscillation is constant, and we're drawing very little current, 0.4, 0.5 amps, and that is really, really nice to see. So if you're at this point, you've done a really fantastic job and the amplifier is probably almost repaired. There's some final checks we're going to do. However, if at this stage you don't have pulses on either bank, then you still have some work to do. In a lot of cases with these amplifiers, both channels of these, both sides, need to be fully functional in order to get pulses on both sides. So even if I had missed something on this side of the amplifier, even though this side was actually fine and didn't need any work doing, you might not actually see pulses on this side just because there's some damage or some issues over here that's preventing it. So if you don't see these pulses on the low side drain, then you've missed something, or there's some damage still in the drive circuit. If you do see these pulses on the low side drain, as we have here, then you just want to go ahead and confirm that everything is equal and perfect. So what we're going to do is probe the gate, the low side gate, this one right here. And to look at this on the scope, we're going to need to zoom in a little bit. And we just want to make sure that the waveform looks nice and clean. It's wobbling back and forth a little bit. That's just because everything's at super low voltage and it's, you know, not really designed to be ran like this. But the shape looks really nice and clean, and we want to make sure that that shape is mirrored identically on the other side. So let's go over to here. So we have that shape there. If I change my trigger mode, it should hold that wave on the screen as I move my probe. There we go. Okay, that's that side, and that's that side. I can see a touch of variance. You see how the VRMS of this waveform is hovering between 8.6 and 8.9 volts. Well, the RMS of this one is a touch higher, hovering between 9.1 and 9.2 volts. Now that's probably just because the drive buffers that I used, I replaced them on this side, maybe a slightly different batch or slightly different model to the ones that are over here, but that shouldn't really cause any issues going forward. However, if the shape looks wildly different between this side and this side, then you might have some issues. You also want to check that the shape on each MOSFET in parallel with each other, so these ones next to each other, is absolutely identical. Now for this, there can't be any variance at all, not even like a touch. So even though we had a little bit of variance between sides, if there's any variance between the MOSFETs in parallel, that's bad news, and you probably have a bad 4148 diode or a bad zener, or you fitted one of the diodes backwards, or your gate resistors out of tolerance or something like that. So that's our low side. Let's go ahead and check our high side now. We need to zoom out a little bit on the scope here. So here's our high side waveform, and let's check that they are looking absolutely identical. Yep, they are. And let's just confirm that with the other side. Let's see how they differ. Again, a touch lower on the other side, but that's nothing to worry about. We've basically got two separate channels, different amplifiers here, and that's no problem at all. Okay, that's looking really good. Last thing you want to check is that there's no DC offset between the speaker terminals here. So we've got 5.9 volts on that one, 5.9 volts on that one. That's looking good as well. And you also just want to go ahead and check that none of the MOSFETs are heating up drastically. You can use your finger at this low voltage and it's fine. You're going to get a bit of heat on them just because there's a little bit of cross conduction, which we might actually be able to change, but that might be for another video. But yeah, provided they're all sort of getting roughly warm to the same amount, then you should be absolutely fine here. Okay, so once you've done those tests, the waveforms look really nice and they have the same amplitude between banks, and they're pretty similar or exactly the same between sides of the amplifier. You're probably safe to go ahead and power the amp up for a full rail voltage test. And in order to do that, all you need to do is either fit the power supply MOSFETs if you haven't done that yet, and move these diodes back into place. So that's what we're going to do now. So with that all back in place, we're now ready for a full power test, and it's always a good idea to have some eye protection ready, because with higher voltages, if the output MOSFETs explode or a capacitor goes or something like that, it can throw debris at your face at ridiculously high speeds. So eye protection is always a good thing to have. Now, I have a thermal imaging camera here. You don't need one of these. I just find it really useful just to make sure that all of the banks of MOSFETs are heating up equally as we power it up. So in order to do a full power test, obviously everything fitted back in, you still need your load on the speaker terminals. These amplifiers hate having no load across the speaker terminals and being idled. So either set your bench power supply to a lowish voltage. I'm going to go for about 9.6 volts first. It just keeps the rail voltage nice and safe and low. Current wise, I'm going to let about 4 amps in. So if you're not using a regulated power supply, try and choose a power supply that is again between 10 and 12 volts, and for this kind of amplifier, somewhere between 5 and 10 amps is ideal. You don't really want more than 20 amps, because if something fails, then that's a reasonable amount of current there that can cause more damage unnecessarily. Now these amplifiers, when they do their health check pulse to build rail, they're usually connected to a car battery which has mountains of current available, so they power up pretty quickly. However, with your limited current supply that you've got connected, it's probably not going to build enough rail voltage when you apply the remote for the first time to actually come alive and for the MCU to be happy about that. So you're probably going to need to pulse the remote a few times in order to build enough rails. So you can stick your oscilloscope probe in the high side drain there, which is going to read your rail voltage. We start off with about 9 volts, which equals our supply voltage. Now every time I pulse the remote here, you can see that the rail voltage climbs up a little bit like that, but it stops. If I hold the remote on, it stops because it detects there's not enough rail not enough voltage present. So I just keep pulsing this, building more and more rail, and eventually it'll get to a point where it decides that there's enough voltage present, and it will begin climbing much faster and powering up. So we're now at that point. The amplifier is going to come alive and start switching, hopefully. So we're going to take our oscilloscope probe, put it onto the low side drain of this channel, and hold the remote on fully and pray that nothing goes bang. Okay, there we go. We have Class D switching, 1.8 amps of idle current, and I'm going to just power it off there for a sec. So that was looking really nice. Nothing was smoking or getting hot. 1.8 amps is nice and low idle current for these amplifiers. I'm just going to go ahead and check that that is equal, the same sort of looking waveform on the other side that didn't appear to be damaged. Let's go over here and check that again. 37 volts DC there, 30, what have we got, 37, 34. 37, 34, the same DC on both sides. That's good. Let's go for another full power up. Yep, that's looking good, and it looks looking good. So we've got 9.6 volts in the amplifier at the moment. So now what we can do is just gradually go up on the voltage from there, which is going to increase the rail voltage a little bit. Going to go up to 12 volts. There we go. Just make sure that that's still fine. I'm going to power off now, and I'm just going to use my thermal imaging camera here just to make sure that there's no sort of like single MOSFETs that are getting much hotter than any others. So these 4 MOSFETs are all getting to about the same temperature, about 30 degrees Celsius. That's looking good. Okay, fantastic stuff. Well, we're going to power that off now, and we're going to let the rail voltage sink out of the amplifier because it's going to be still in the rail caps there. Be careful, once you've powered the amplifier off, you've still got high voltage rails probably sitting in there. How much we got left in there now? Still got 50 volts there in the rail, so just let that dissipate itself, or you can short it out with like a 20 ohm resistor or something to ground, and then we're going to reassemble it back into the case, do some endurance testing, leave it idling for a couple of hours with the load connected just to make sure that you get all the chips up to temperature, make sure everything's fine while it idles, then run some power through it, make sure that it's happy making power as well, and then it should be good to go back to the customer and hopefully give them plenty of years of bass. Let's put some fresh thermal paste on these new FETs. So we're back in the case, everything is reassembled, we're powered up, we've got a bit more current on tap now. I'm limiting this to 20 amps, this is a 40 amp supply. But to drive this to mechanical limits free air, we don't need 40 amps. So let's just see how it goes. Let's start cranking up the input level here. Woo! That's It's going strong. It's moving some air. Let's turn the frequency a little bit. There we go. Get that rolling shutter effect. Yeah, that is performing really nice. So we need to do some endurance testing and some higher power testing on resistive loads. And provided it passes that, this amp is ready to go. So guys, I hope that you enjoyed that, and bear in mind that you can use the information in this video to repair not only the SFB range of amplifiers, but also all the others that I've listed and also detailed in the video description. Also in the video description are all the parts you will need, all the different MOSFET models and tips that you'll need to change out parts in these and make sure you're putting parts in that are compatible. If this was useful to you or just entertaining, feel free to leave a like and a subscribe. It does help the channel a lot. But yeah, I hope you enjoyed, and I'll catch you in the next one.